provided by the ICTP-SAIFR. So please go ahead and when you have the time, you can sign it here, so on the table here. And we have the second lecture by Professor Pierfrancesco Urbani now.
Okay, so the idea for this lecture is that okay, yes, now it works. So the idea is that, so last time I essentially discussed what happens if you look to numerical simulations and gave a kind of overview of a set of very interesting observations that you see when you look at the Jammine point of our spheres. And now I would like to tell you how one can construct a theory for the Jammine transition in the limit of infinite spatial dimensions. Now, I will not derive all the details. I will just tell you the essential ingredients. And I will tell you what's the outcome of the theory. And then the idea is that I would like to map the problem of Jammine transition of our spheres into another problem that is a constraint satisfaction problem that we discussed yesterday. It's a broad class of broad class of problems to which jamming belongs to. So I will introduce a simpler model that can be solved a bit more easily, and it will be the subject of the next two lectures. So, so let's start from the infinite dimensional theory for simple glasses. So yesterday what we discussed is that if you take our spheres and then you run some kind of Newton's dynamics and you slowly compress our spheres, you get a phase diagram like this. So you have 1 over the pressure here as a function of the packing fraction. And at low packing fraction, the system is in a kind of liquid phase. And then at some point, the relaxation time becomes very large. And effectively, the liquid becomes a glass. So it's still an amorphous structure, so there is no crystalline order. But if you look at all properties, like shear modulus and so on, you start to see something which is fine. So you get a solid. So at some point, you get a glass transition. Okay. And then when you have this glass transition, so first it depends on the protocol that you use. In 3 dimensions, depending on the compression rate, you have a glass transition that can be at high phi or low phi. And then as soon as you hit this glass transition, essentially your equation of state, that here is the equilibrium equation of state, changes, and you get stuck into a glass. And then when you compress this glass, at some point, you reach the jamming point, which is the point where the pressure diverges. So our spheres get in touch, and you cannot compress the system anymore. And so you will have a lot of curves that depend on the way in which you compress your system, your liquid. So the slower you compress your liquid, the higher the packing fraction at which you leave this equilibrium equation of state. Okay. So this is what you get if you do some simulations in 3 dimensions. And now you can look at what happens if you take the infinite dimensional limit. So how do you construct a theory for glasses in infinite dimension? So the main idea is essentially to start from the theory of liquids. So there is a nice book by Hansen and McDonald. Book. But essentially, they use tools from field theory to get, for example, the virial expansion diagrammatic expansion and so on. So you get and so on. So it's a set of tools that you can use to study this liquid phase. And then the idea is to merge this with theory, mean field theory of spin glasses. And the reference book is the one by Mézard, Parisi, and Virasoro. So, and here you get a set of ideas like quench disorder, replica method, replica, and cavity method. Free energy landscapes. Escapes, and so on. So the idea is to take both tools and merge together. Now, what's the problem when you do this? The problem is that, I mean, if you take spin glasses, those are systems in which you have the degrees of freedom that interact between themselves via some random couplings. So you have what people call quench disorder. And in these systems, there is no quench disorder. So if I take a bunch of hard spheres in 3 dimensions or 4 dimensions, whatever dimension you want, there is no quench disorder. So all the techniques that have been developed in this field really rely on the fact that you have quench disorder in the game. And in order to average over quench disorder, you need to introduce replicas of your system and so on. Here, there is no quench disorder, so it's not clear how you can adapt the techniques developed in this field to this one. So it took a lot of time to develop such techniques. And the main idea, so one of the way in which you can apply those techniques in a context where there is no disorder comes from an intuition that we have about glassy states. So to a first approximation, if I think about a glass, this is a kind of amorphous structure in which particles just vibrate around some reference position, and this reference position is some kind of random position in space. So overall, the structure is amorphous. It's just that the particles cannot diffuse, they just vibrate. And instead of vibrating around a crystalline lattice, they just vibrate around some random lattice. Okay? So if you think about a glass, so you have spheres that just rattle around. They are inside some cage that is formed by the atoms. And that's it. So I don't know, this drawing is not very good, I understand. Okay, so if you want to describe a glass, what you can do is really to try to describe the vibrations of particles around some reference configuration. And how do you choose the reference configuration? So the simplest way to choose the reference configuration is just to say, OK, I extract a configuration since, OK, let me say this way. So I can choose as a reference configuration a given configuration at a given time of your particles. So I took this as a reference configuration. And then say, OK, for all times after the time that I choose to take this reference configuration, particles will move around the point that I've chosen. Okay. So this construction has a name. It's called Franz Parisi construction. Actually, it's a potential, so it's called Franz-Parisi potential. And this was developed first in the context of spin glasses, where you have quench disorder. So in principle, you could use the techniques that you have when you have quench disorder. But it's nice because it applies also to systems where you don't have quench disorder. So how does it work? So imagine that you have this reference configuration. So just let's start with some. So I will call xi, so the position of particle I. So this is a vector in d dimension. So this is supposed to be a d. Okay. And then I will call big X the set of coordinates of all the particles. Okay. Okay, so let me call Y the set of coordinates of the reference points. Okay, so I will call them yi. Again, these are d-dimensional vectors. And for the moment, let me assume that this is fixed. Okay. So if you want to study vibration around this reference configuration, and the system is at a given temperature, so what you can do is that you can just define a free energy, which is a function of all your control parameters, the temperature, packing fraction, the strain if you want, if you add a strain to your system, whatever control parameters you have, and the reference configuration. So it's a free energy because I imagine that the vibrations given this reference configuration are at equilibrium. So I will write this free energy as, okay, let me just write the extensive. So, okay, and so what is this? It's an integral over all the configuration of the position of the particles. Then I have a Boltzmann factor. And this depends on all your control parameters. So phi, gamma, whatever. Gamma is just a variable that can, for example, you can use it to denote the strain or whatever other control parameter that you have. So this is the free energy of the system. And now I want to constrain it to be close to the reference one. So how do I do? So since I want to have the system X to be close to Y, I need to define some measure of similarity between X and Y. So let me define this measure, the mean square displacement. I called it delta R. Okay, no, let me call it delta. Okay, so this is, if you can think about it as a kind of measure of the distance in phase space between configuration X and configuration Y. So in particular, this is 0 if they are the same. It takes a finite value if they are a little bit different. Now, I can use this to enforce that this free energy is computed only when X is at a given distance from Y. So I allow the configuration X to be at a fixed distance from Y. So how do? I just impose a delta function. And I say, OK, I want that the system X is at distance delta R from the system Y. So it's so what is this? This is a constraint free energy. And in particular, here it depends on, where do I write it? Here, delta R. Okay? So now you see that you start to see some kind of quench disorder in the game. Why? Because if I look at this free energy, you have that the configuration Y is random because I extracted it in some way. So from the point of view of the configuration X, this is a kind of Boltzmann measure with some quench disorder inside. Okay. And now, since I would like to study some typical property of a glass, what I need to do is to consider a typical configuration Y. So I would like to take an average over Y, because I would like to measure this free energy when I extract a typical Y. And a typical Y, I just need to average over it. So I would like to average this, so I denote with this the average over Y. And which measure do I choose? Well, it's reasonable to think that, if I'm able to equilibrate a glass, for example, here, so this reference configuration is the configuration at which the glass falls out of equilibrium. So at this point, I'm at equilibrium. So the average over Y will be a Boltzmann factor. So this is the partition function. And then here you have the control parameters. Okay. So I would like to average with this measure this free energy. Okay. So I would like to average this term. And so this is the average of some log. And so it's precisely the same problem that you have in spin glasses. Okay, I didn't discuss spin glasses, but that's how replicas come into the game. Because now, okay, I will not tell you the details, but so how do you average a log? So you use the replica trick. So you say that log, okay, maybe I will not tell you this detail. But okay, so I will tell you later. So what this construction tells you is what's the typical free energy that you sample with this measure, and where you impose that the configuration of the glass are at a given distance from the reference configuration. Now, all this construction depends on this parameter. Okay? So how do you choose it? So since this is a free energy, what you would like to do is that you would like to minimize with respect to your parameter. Okay, so you expect that the system is trying to minimize the free energy. So you can say that the thermodynamics of the glass, so the restricted thermodynamics of a glass, is described by a value of delta R, which minimizes this average. And so what happens is the following. So if phi is low, so by the way, this thing is what is called the Franz-Parisi potential. So the average of this object is, I will denote by VFP. It's a function of delta R and, of course, all the control parameters. And now I can plot V as a function of, let me plot it as a function of 1 over delta R.
Pierfrancesco, can I ask something?
Of course.
In the spin glass case, for instance, you have all those issues about the free energy being self-averaging.
Yes.
You have the same kind of
Yes.
subtlety here that
Yes. You have the same transitions. And actually, the fact that in spin glasses you have the same kind of transitions that you have in glasses, at least in the mean field limit, it was kind of dreamed by Kirkpatrick, Turumalai, and Walliness, who were working on spin glass models, a certain class of spin glass models, that they looked, it behaved like structural glasses. And they conjectured that those spin glasses were in the same universality class of structural glasses. So I will tell you what are the transitions, but you are totally right. So all the issues that you have in spin glass theory about free energy and so on, you get in structural glasses. Yes? Okay, so for our spheres, this measure is essentially 1, provided that the spheres do not overlap. Okay, so you allow just configurations where spheres do not overlap. But if you have like soft spheres, those are thermal systems, so it makes sense that you have some temperature. So I just wrote the most general thing. But for our spheres, you need to, I mean, H is infinite as soon as spheres overlap. So this becomes like a theta function on configurations that respect the constraint. So now you can look at this, this potential. So when, okay, now I will discuss about hard spheres. So my control parameter is not temperature, but everything goes the same with the temperature. Now for hard spheres, the control parameter is phi. And you can look at the shape of this Franz-Parisi potential when, as a function of delta R for different phis. So it happens that if you take phi that is low, so you are in this liquid phase, the shape of this function is like this. And you have just a global minimum when delta R is infinite. So what does it mean? It means that the system X doesn't feel the presence of the system Y, because the typical distance, which is the one that minimizes the free energy, is infinite. So it's like the two systems don't talk to each other. Now, when you increase phi, so you go to the denser phase, it happens that the shape of this thing does like this. And then at some point, it develops a saddle. Okay? And then if you increase phi, at some point, you get a local minimum. So what does it mean? It means that there is a large deviation, because this is a metastable minimum, where the system X is trapped by the system Y. And so the two systems stay close to each other. And the value at which this happens, I will call delta EA. So the point at which you develop this saddle is called, so this line, let me, so this happens at what is called the dynamical grass transition, or MCT point. And the value at which, the value of delta at which you develop this metastable minimum is nothing but the typical size of the cage in which particles get trapped. Okay? Now, all the infinite dimensional business is how you handle this formula in the limit of infinite dimension. And this I will not do. But the idea is that you start with this construction, and then you exploit the fact that when the dimension is large, everything is controlled by a saddle point. Okay. So this is interesting because it gives access to thermodynamics of glassy states, that can be interpreted as kind of a free energy restricted to some portion of phase space. So with this construction, you can look at the properties of this local minimum. This will tell you the properties of a glass. Okay? And okay, so let me just write the phase diagram. So again, I take R spheres. So at low phi, you have a global minimum at 0. And then you have this dynamical glass transition here. Where you have this local minimum appearing. Now, one can do, I mean, what I would like to do is just to write a cartoon of what happens to the phase space when you cross this point. So in this region here, I will write some kind of high-dimensional phase space this way. So this is the phase space of all configuration of the system. So here you are in a kind of liquid phase. So particles can diffuse. And so they can explore all phase space. Now, when you cross this point, you have the appearance of this metastable minimum, which represents the fact that if you look to the phase space here, it is clustered. And if I start my dynamics in one of these clusters, I'm able just to explore this one. And only on exponential time scales, I'm able to jump from this one to another one. And this jump is the one that gives you a global minimum in 0. But if you forget about this jump, as soon as you start your dynamics inside one of these classes, you will stay there forever. So when you cross this dynamical glass transition point, this corresponds to a clustering transition in phase space. Okay, so you cannot explore phase space ergodically. The only thing that you can explore ergodically is just one component. And you have exponentially many of these components. Now, if I take one component here at a given density, I can play the game of compressing it. So I start, for example, by sampling the reference configuration Y with this packing fraction. And then I can consider the system X and compress it. So the control parameter phi here may be different from the one here. Okay? So this will correspond to prepare a glass at a given packing fraction. Let's call it phi g. And then I can use the system X to explore what happens to this glass when I increase phi, starting from phi g. And so this will allow me to reconstruct the equation of state of a glass. Okay? And this you can do, again, in the infinite dimensional limit, where you can control this expression. And actually, you can both compress the glass and even decompress it. And so at some point, you will have a melting transition. So this is where essentially you melt back the glass into the liquid. And depending on your initial density, you have many equations of states. And in particular, the more stable the glass is, the longer the equation of state is. And this you get from the computation. Okay. So I told you that each line corresponds to what happens to one of these clusters in phase space when you perturb it. Now it turns out that, and that's the new thing that, so just to come back to your question, so this phase diagram you get also for spin glasses. Particular, there is a class of spin glasses that exhibit one-step replica symmetry breaking, dynamical one-step replica symmetry breaking. And this means exactly this. So this dynamical glass transition, you can have exactly in the same way in spin glasses. So examples are p-spin models or Potts glass. So as an example, so in this case, you have an Hamiltonian, which is a random Hamiltonian in which, for example, you take those spins to be Ising variables, and then the J's are Gaussian random variables where you have to tune properly the variance in order to have a well-defined limit. So everybody is connected to everybody, and the interactions are three-body interactions. So this model has exactly the same phase diagram as this one, as our spheres, apart from something that arrives close to jamming. So this model, for this model, there is no jamming transition because the energy cannot be zero. But all what happens at, let's say, finite pressure is the same that, as here. And this was, I mean, I think it was really something that it was a breakthrough in the end, because this was realized by Kirkpatrick, Tirumala, and Wollins in a series of papers in around 87, 89. And this gave birth to random first-order transition theory. So all the time after their work, it was essentially employed to try to understand how this scenario could be applied to real systems where you don't have quench disorder. And now we know that in the limit of infinite dimension, they were right. Okay. So it was really something that was very important. So the main thing that happened, and that you can have also in this model, but there it was not realized in its importance, is that you can have an additional transition where, when you look at the equation of states of these glasses. So remember that here you have a jamming line. So this is phi d. So, OK. So here you have a jamming line, which corresponds to the point in which, when you compress those glasses, at some point the pressure will diverge. Okay, so the jamming transition depends on which glass you are looking at. So this is the J line. And so what we found in 2013 is that if you look at the equation of state of these glasses, you realize that there is a new phase transition before you hit the jamming transition. OK, so let me just write a line, and then I will comment. So there is a new phase transition that it's called Gardner transition. That separates those lines into two pieces. So above this point, we say that you are in the normal glass phase. And below this point, you are in the marginal glass phase. So what does it mean? So let me just take a step back. So if I look at this transition tells you that you come from a phase in which the system can explore ergodically all your phase space. And then you enter into a phase in which the phase space is clustered. Now, if you look at what happens inside one of these clusters, upon compression, you can get exactly the same phenomenology, but within a cluster. So if I take one of these, so when you cross this Gardner transition, each cluster that you can think that it was kind of meta-basin in your free energy landscape starts to have a structure. And it gets, so this blob now is just this blob. And then it starts to have some structure inside. But now the structure happens on all scales. Okay. And so this is what is called replica symmetry breaking, which is what was found in spin glasses in the 80s. And here we have exactly the same thing, but in systems without quench disorder. And so this transition happens before the Jammine transition. So if you want to describe the Jammine transition, you need to take into account these replica symmetry breaking effects. Yes?
So is this like infinite step replica?
Yes, this is infinite RSB.
Series of higher replica symmetry breaking, or is it one infinity?
Sorry?
Is it one step replica symmetry breaking as the dynamical one?
Yes, so this is one step replica symmetry breaking, dynamical.
And then it's just infinite after that, or is there a hierarchy?
No, there is no hierarchy. So you can have something happening here, but OK. I mean, this really depends on the system that you look at. What happens is that as soon as you go close to the J point, RSB becomes infinite RSB. So you have an infinite structure of clusters, and so on. OK, so and this was what was found and solved by Parisi in spin glasses in the Sherrington-Kirkpatrick model. So here we have the same. And what is striking here is that if you want to describe the Jammine transition, you really need to take into account those effects. So if you don't do it, all the observables that we discussed yesterday, you don't get them. So you get, for example, wrong critical exponents. You don't get isostaticity. So it's really crucial to have all what is observed. OK. So just last word. So this Gardner transition is a replica symmetry breaking transition within a glass. OK, so more or less, this is what I wanted to tell you about the infinite dimensional solution of structural glasses. And now I would like to go back to the original perspective of constraint satisfaction problems and try to map this problem into an abstract one, which can be solved much more easily.
Francesco,
Yes.
as soon as you have this minimum in the Franz-Parisi potential, all minima are equally good, or is there any minimum which is more relevant?
So, OK. OK, I was a bit sloppy here. So what happens when you cross this dynamical transition is that you have exponentially many minima. And for each phi, there is just a given subset of those minima, which is exponentially large, which really contributes to the Gibbs measure. So above this point, you have a complexity. Okay. So above this dynamical transition, you can look at the log of the number of clusters with a given internal entropy. So I just count all configurations that are inside the cluster. I take the log of this number. This is the internal entropy of the cluster. And then I count how many clusters I have at that internal entropy. Okay. And now we'll get. So this is, again, this is the log of the number of clusters whose internal entropy is S. And what happens is that when you cross this point, so you have exponentially many clusters. So this is finite. So I need to divide this by n, the number of degrees of freedom. And then this has this shape. So you have exponentially many clusters, but so, okay, so, yeah, so this is at a given phi. So I fix phi, and I look at this number. So this tells me that I have exponentially many of these. And then if I look at the Gibbs measure, the Gibbs measure is dominated as soon as I cross this point by those states. Okay. Then I can move phi, and then you can show that the Gibbs measure is not always dominated by those states, but the states that dominate the measure can change. And in particular, when you increase phi, you have that the states that dominate the measure can change, and at some point you get an entropy crisis in which the states that dominate the equilibrium measure are no more exponentially many. And when this happens, you have that this local minimum becomes the global one. Okay, so this is the Kautzmann transition, which is realized in infinite dimension. Okay. So all this is, so now that, I mean, just, there is a book that we wrote with Giorgio and Francesco, where we review all the construction. Okay, but I do not want to do it because it's a bit lengthy.
There's a question here.
Yes. Yeah.
So I know that in the Sherrington-Kirkpatrick model, there's like a symmetry between the minima, where, you know, like a reflection. If you flip all the spins, that's also min. Is there sort of an analogous symmetry between the minima?
No. So if you take SK, so this model is just with pairwise interactions, and it's all-to-all. So this is invariant under Z2 symmetry. So if I flip all spins, it's get the same energy. But in glasses, this Z2 symmetry has no meaning. And indeed, I mean, if you are inside a glass, there is no other symmetry than replica symmetry, which I didn't introduce for you, but I will do it later. So this Gardner transition, indeed, is a replica symmetry breaking transition in a field. So if you take the Sherrington-Kirkpatrick model and you add a field, okay, I need to use another letter. So this has no more Z2 symmetry, but this model has a replica symmetry breaking transition. And since it's an RSB transition without any other symmetry than the replica one, it's in the same universality class of the Gardner transition. Okay. So this transition that you hit here is like SK model in a field. Okay. There was another question there.
Just a simple question, but I haven't understood until now. What is the mathematical meaning of taking the dimension going to infinity in theory for simple glass. It's a kind of asymptotic expansion of observables. What is this very strange limit, the space, time, the dimension going to infinity? Do you have any clue to get some physical
Yes. Okay.
sense of this?
So what happens if you are in infinite dimension is the following. So imagine that I have a particle, A, that is in contact with another particle, B. Now, what happens if I add another particle in contact with A? If the dimension goes to infinity, the probability that this new particle that is in contact with A, let me call it C, touches B, is going to 0. Just because if I'm in infinite dimension, I mean, the probability that all these three are in contact just goes to 0 because the dimension is very large. Yes?
But you could get corrections in the expansion one.
Yeah.
I'm thinking that in certain sense make an expansion on powers of 1 over D.
Yes, you can do the expansion in 1 over D. Yes, you can do, but it's very complicated. So nobody did it for the moment.
Nobody has done that.
No, no.
But what is the problem?
I mean, what happens when you take large D limit is that this expression, okay, I will say something. So you can write some virial expansion for this thing. So I will write something that will not resemble this expression.
This is the free energy.
Yes, the free energy. So you write the virial expansion, and the virial expansion is a function of some local density of particles, and this takes the following form, where rho is just the density around point x. And then you have a term here, which is a two-body term. And here you have something which is called the Mayer function. Okay, it has an expression, but don't worry. And then in principle, you have here three-body terms and so on. So when you are in large D, since the probability that B and C touch goes to 0, all those terms, just you can remove them. So you can show that they are exponentially suppressed in dimension. But now, if you allow the dimension to be large but finite, you have all of them. Okay? So in principle, you can take into account 1 over the corrections, but this is complicated.
In a possible microscopic theory, if you have a microscopic more detailed theory, you could make mathematically well-defined the expression 1 over D.
Yeah, the mathematical is well-defined. Yeah, it's well-defined. It's well-defined. It's just that it's hard to do.
That's an effective theory. The spins class and that's effective theory from one microscopic theory, whereas you define the expression of the day well-defined.
Yeah, so in general, if you want to have really a theory, for example, around this point here, so around the dynamical gas transition, so this is a sharp transition only in infinite dimension. So as soon as you are in finite dimension, this is a crossover. It's the mode coupling crossover. And in order to study this crossover, you need to include not only 1 over D correction. It's not just computing the 1 over D correction. Here you have non-perturbative corrections that are just due to the fact that now you are not constrained to be inside one of those clusters, but you can jump with finite probability. Yes. Yeah, so all these things, for example, the fact that you have exponentially many metastable states is something that can live only in the infinite dimensional limit, apart from the point where you get this Kautzmann transition. So this can live also in finite dimensions. But this phase in which you are dominated by exponentially many glasses, this can live only in infinite dimension. In any finite dimension, this is an approximation, which just neglects the fact that you can jump from one glass to the other. So in order to derive this, I need to assume that if I start here, I will not go to any other glass. And I can study the restricted thermodynamics of one of those clusters. So it's an effective theory, and for this, it gives you something. For example, you can analyze dynamics. You can analyze, for example, dynamical critical exponents close to the mode coupling transition in infinite dimension. You get some answer that is not very far away from what you get in 3D. So it's an effective theory. You understand why it's an effective theory, but it gives you also some reasonable thing. And then the striking thing happens when you look at jamming. Because at jamming, okay, maybe Jim will say that the upper critical dimension is 2, but at jamming, if you compute the critical exponents that I was mentioning yesterday, you get values that agree very well with numerical simulations. And we believe that they're, okay, at least if you have some finite dimensional correction, must be very tiny. And we don't see it for the moment. So for jamming, all this construction is good in the sense that you get very quantitative results. So you don't need to go to do 1 over D. Okay, so this is what I wanted to say about infinite dimension. How much time do I have? 40 minutes. Ah, that's great. Okay, so I want to go back to the perspective that we looked at yesterday, the one of constraint satisfaction problem. Yes.
Quick question. So the DFE under the Gaussian transition is basically not a good representation because we have the.
No, it's a good representation, but in the end, here you have a simple order parameter, which is just this delta R. So you can think about delta R as a kind of magnetization. So if you take the Curie-Weiss model, you have the high temperature phase in which the free energy has just one minimum at 0 magnetization. And then when you go below the critical temperature, you develop 2 minima, one of magnetization plus and the other magnetization minus something. And this is the same. Now, when you cross the Gardner transition, in addition to this, you have an order parameter which becomes a function. Okay, and this I will tell you maybe tomorrow. But the order parameter is more complicated because, it essentially describes all this structure. So if here you have just one cluster, and this is defined by this delta R, or delta EA at the minimum, here you have many clusters, one inside the other. So it means that you have many deltas. Okay? And in the end, you get a function where X is some kind of hierarchy in this construction. So now X is not any coordinate. It's a coordinate in this construction. Okay, it's kind of abstract, but I will explain tomorrow. Okay? So I think that there was G. Okay.
So I just wanted to mention this basic problem has been around for a long time, and watching these people do pretty complicated things and get things that really work down to 3 dimensions and see are given numbers agreeing with 3-dimensional simulation. It's not new that you can do something in infinite dimensions and have it work down to low dimensions, but it's amazing that they did it for glasses.
Look, I think that what I find striking about this, and I don't understand, by the way, is that, typically when you do mean field theories, you get rational critical exponents. So I don't know, if you do ferromagnets, you have 3/2, 1/2, and so on. And when you compute the exponents at jamming, you get something which is probably irrational, and it comes from a non-trivial scaling theory. So it's a complicated construction. You get some numbers that are not what we are used to when you do mean field theory, and they seem to work. So why they work, I'm still not. But it works. I mean, it works in the sense that if you compare with numerical simulation, they agree. They agree. I would like to be agnostic. I'm always try to be safe. So it works with numerical simulations.
I'm just putting the glass mostly full instead of completely empty.
Okay, so what I want to do is now to go back to the constraint satisfaction perspective. So by the way, this Franz-Parisi construction is one way to get the properties of glasses. So really to compute the restricted thermodynamics inside one cluster. There are other methods. For example, there is one that was devised by Rémy Monasson that is slightly different, but in the end you get the same thing. So this one, I think it's, the Franz-Parisi one, I think it's particularly simple, not simple, but clear, at least in my mind. Okay. So let me change again the perspective. And go back to constraint satisfaction problems. So we started with the packing problem. So, okay. So these are class of problems that are studied a lot in computer science. So example are KSAT, which I will not write. Another example is coloring. So in coloring, you imagine that I give you a graph, which you have nodes and edges. So the graph has some connectivity C, so it's how many edges you have per node. And then the constraint satisfaction problem is to try to color the graph in such a way that, so you are given Q colors. And then you would like to color the graph in such a way that if I take one edge, the colors on this edge must be different. Okay? Now, if the connectivity is very small, you can imagine that it's very easy to color the graph. And then as a function of, if you fix Q, when you increase the connectivity, at some point you cross a transition in which the graph essentially cannot be colored. Okay? So as a function of, I'm coloring the vertices. So I have Q colors, and then I would like to color the vertices in such a way that for each edge, the two vertices have different color.
Okay.
So as a function of C, at some point I have some SAT and SAT transition. So there is a SAT phase, and there is an unsat phase, which looks like the jamming problem, right? So if you think about jamming as a kind of constraint satisfaction problem, this is another problem that looks like jamming in spheres. And actually, this was something that was analyzed early 2000. So there is a book by Mesar and Montanari, where they summarize the methods that you can use to study this problem. So this problem has some randomness. Why? Because typically what you do is that you extract your graph at random. So you, for example, you fix the ensemble of graphs, like Erdos-Shreni random graphs. You pick one of them, and then you ask the question of coloring this graph. So there is some randomness inside the problem where you can take the average. And so there are all the techniques coming from disordered systems that can be applied to this case, except the fact that here the graph is not fully connected. It's a kind of random graph. So mean field theory is a bit more complicated. Actually, it's much more complicated. And there is this book where they summarize what you can find. And in particular, what happens is that in this SAT phase, you have essentially the same transitions that I've been discussing for hard spheres. So you have a dynamical transition, which is a clustering transition, and then all sorts of things. Okay. Now, so you have many problems of this kind. And those problems are important in computer science because people use them to discuss computational complexity. And so the problem with jamming is that it's a bit different from this class of problems in the following sense. So here, you see that the variables are discrete. So you have co-colors. And so when you cross this point, essentially you go from a phase in which you have 2, 3 solutions, 1 solution, and at some point I jump to 0 solutions. But this jump is kind of discrete. Okay? So you have, as soon as you increase C, so imagine that I have a graph and then I start to add links. So if I do that, I kill solutions, but the way in which I do it is kind of discrete. If you think about hard spheres, this is not the case, because when I compress, the space of solutions changes in a kind of continuous way. So it shrinks in a kind of continuous way. So you have a volume of solution, which is a number, a real number. And then this goes to, okay, it's not 0 because you have continuous variables. Okay. It goes to 0 when you reach the jamming point. So if you want to discuss jamming, you need to consider continuous constraint satisfaction problems. So there are problems in which you have continuous variables. So the volume of solution shrinks continuously to 0. And this is important. Why it's important? Because if you have something which goes to 0 continuously, you can have the emergence of scaling. So in other words, if I look at my system at the jamming point minus epsilon or minus 2 epsilon, it may be that these 2 points, the space of solution look the same as when you do RG close to the critical point. Okay? So you can have that scaling emerges only if you have this property, essentially. And this is what makes jamming different from those problems. Okay. So if you take this perspective, then you can define other constraint satisfaction problems for continuous variables. So let me introduce the simplest one. So the simplest one is the perceptron. So this is a model that comes from machine learning. And let me tell you the origin. So the origin is supervised learning. So imagine that you have, so probably you do some machine learning, or some of you do some machine learning. So imagine that you have pictures of cats and dogs, just not to be original. So these are cats, these are dogs. And then you would like, so you are given a data set. So each picture of a cat or a dog is some vector of pixels, for example. So this vector is high-dimensional, because if you take an image, you have a lot of pixels. So let me say that it has n coordinates, and this n is very large. And now you would like to have a function that such that if you give the function this vector, it tells you if this vector is the picture of a cat or a dog. So how do you do? So the simplest function to do that is a function that tries to do some linear separation between these two clouds. So it tries to construct an hyperplane that separates these two clouds of vectors. So what is this function? So imagine that I say that a vector is a dog, and I assign a label to it. So this is a vector xi mu. And the label y mu is 1 if I take pictures of dogs, and -1 if I take pictures of cats. So you would like to construct a function, f, that takes as an input the size, okay? So it takes as an input size and gives you the corresponding y. Okay. So what's the simplest function? You just take y mu, that is the sign of the scalar product of xi mu times some unknown vector, w. So this vector is just telling you what is the position of this plane. And for each picture that you have in your data set, so for each vector xi mu, you would like this equality to be satisfied. So this must be true for all mu. And let me assume that you have many of them. In particular, you have m images of cats and dogs. Is it clear? So maybe you are familiar with this. Okay.
The vector could be like, can I imagine that each image is pixels, and then you have zeros and ones?
You have zeros and ones. So this is size. And then you would like to find a vector that is n-dimensional, because this is n-dimensional, that such that if I fix this vector, I get this equality to be true for all pictures in my data set. Okay? So if I just take one picture, then it's very easy to find w. But if I have many pictures, then it may be complicated. Okay. Now, let me just rewrite this thing in a more clever way. So I can multiply, since y mu is plus or minus 1, I can multiply everything by y mu. And so I just get 1 equal to the sign which means that y mu equal to 0, it will not happen, but okay, so you can say that you want to be positive. And this must hold for all mu. So you have a system of inequalities that I want to solve. Now, this problem is a bit ill-defined in the sense that you see that if I rescale by a positive number the length of the vector y, nothing changes. So it makes sense to say, okay, let me fix the length of the vector y to be a constant. And without losing generality, I can say that the length of the vector y is n, which is the dimension of the system, which is nice because this means that typically the components of these vectors are numbers of order 1. Okay, so you have so this vector is the weight vector that you need to find in order to perform this classification task. Okay. So this is your phase space. It's the hypersphere in n dimension. And n is very large, so it's very high dimensional. And then you have a bunch of constraints that are inequalities. Now, so this is a continuous constraint satisfaction problem because those variables are real variables. And then starting from this, you can generalize it. So since we don't have any structure in the problem, so if I take a glass, it has no structure whatsoever, so it makes sense to ask this question, but with completely random vectors, xi mu's, and y mu's I can even remove, because as soon as this vector is random, whatever thing I multiply, which is plus or minus 1, it's not important. So you can think that you take these vectors, xi mu's, and you imagine that those components are random variables that are Gaussian with 0 mean and unit variance. Okay, so I extract m random vectors, and then I ask myself, okay, I would like to find a configuration W such that this scalar product is greater than something. And now, since those are random numbers, I need to rescale this by root n, because the components of this vector are of order 1. The components of this vector are of order 1 because I'm choosing this normalization. So by central limit theorem, this scalar product is typically of order square root n. So if I divide it by square root n, I get something which is of order 1. So my CSP, my constraint satisfaction problem, will be the following. Try to find a configuration W, that satisfy those constraints for all mu's. And sigma is a control parameter. So this is very abstract. And let me try to make the parallel with spheres. So since you have n dimensions, in order for the, if you want a problem that has some interesting behavior, you need to have that the number of constraints at least scales like the number of degrees of freedom. Because if you have many more degrees of freedom than the number of constraints, it's very easy to find a solution to this problem. So you would like that the number of constraints that you have, that is m, scales with n, and I will assume that it scales linearly with n. So you have order n constraints and order n degrees of freedom that are the coordinates of this vector. And this alpha is another control parameter in the problem. So let me just make the mapping between the perceptron and spheres. Okay. So if I look at the degrees of freedom, here I have the vector W. Okay. And here it's just the set of positions of spheres. Okay. Now, so for spheres, the relevant variables were the gap variables. So you remember we defined this hij, which is just the distance between sphere I and sphere j, and then I remove the sum of the radii. Here I can define a gap variable, because I can just say, so, and for spheres, you want it to have this thing to be positive. Okay? So here, I can just define a gap variable, which is just this scalar product minus sigma. So if you look at it, I mean, they look similar. I just replaced this function, which is nonlinear, with something which is linear in the degrees of freedom. Okay? And then you see that the role played by the sum of the radii is just played by this control parameter sigma. So, I don't know, diameters, radii. Now, for spheres, we said, OK, we would like to solve the packing problem, so let's define some Hamiltonian. So what you do is that you say, OK, I take H, that is a sum over pairs of spheres of some function of the gaps. For example, you can take the harmonic cost function for harmonic spheres. You can take R spheres, whatever you want for this V. And here you can do the same. So you sum over all gaps of some function that you choose. Harmonics of spheres, it's a good function of this gap. And then the last thing is the density, or packing fraction. So here it's phi. Okay, so how many spheres you have in the box. And here it's just the number of constraints that you have. So it will be this control parameter alpha. So increasing alpha, it's like increasing the packing fraction. Yes?
So in the perceptron problem, the idea is to find like what W defines the hyperplane, right? And we assume that it exists. Like you can find the hyperplane that.
Yeah. So okay, exactly. So what happens is that so as here, when you increase phi, at some point you cannot find a satisfiable configuration. Here, if you increase alpha, at some point, I mean, since those vectors are random, you will not be able to find a solution. Okay. Of course, now these vectors are completely random. If I take pictures of cats and dogs, they are not completely random. There is some direction that separates the two. So you can, for example, think that those vectors are like Gaussian clouds centered at two positions. And if I have anyway many data, there will be some tail of one cloud that goes in the other side. So there will be some alpha star such that at some point you are not able to find this plane. So you will have what people call interpolation threshold in machine learning, which is like a jamming transition. It's not like a jamming transition because here, I mean, it's not a critical point, but okay, it's a critical point, but not with the properties of our spheres. But this really depends on the fact that this machine is too simple. If you just take, I mean, you can redo all this with more complicated networks. So for example, instead of taking the perceptron that is this, here you take some function of function, which is a two-layer network. And then you can play exactly the same game. And say, OK, now I have a two-layer network. This defines a function. And now I would like to find the sets of weights in this neural network that satisfies this learning problem, so the fact that I get the right assignment. And there I will get some jamming transition. Why? Because this problem will be non-convex. So this, I will come to that.
If I understand correctly, you're replacing the hyperplane with the n-1 dimensional surface? Or?
In the case in which you have real pictures?
No, I mean with the multiple layers. Are you replacing exactly with a field? Or?
Oh, yeah, so when you do multi-layer, it means that you have two sets of vectors. For example, imagine that you have two layers. So here, I mean, you can write this as a kind of, so typically people write this like this. So these are the, I don't know, maybe visible variables, I don't know how people call them. So these are the components of the vector size. And then you denote by these connections W1, W2, Wn, the components of the vector. So this function is just the product of the components of the vector size times the components of the vector w's. So this is the simplest architecture you can think about. But then you can do something else. You can do something like this. Here you do some connections. And then you have two sets of weights. So you have, let's say, W1 and W2. And then you can define a more complicated function. This more complicated function will not perform a linear classification. You are allowed to have some curvilinear classification in a dimension. I don't know how to say. And this will be, so for some class of these things, of neural networks with one hidden layer, you can reach a kind of jamming transition. And this will be in the same universality class as spheres. OK, so this was, so we did a paper with Silvio, Sungmin Wang, and myself. It's 2019. But this is complicated. So we analyzed just one hidden layer neural network. Now, I will not talk about them, because everything can be done in this simpler model. OK. Other questions? OK, how much time do I have? 5 minutes. OK, so I would like to tell you one last thing before we stop, which is the following. So, OK, so I defined this problem. Now let me try to look at it from some kind of geometrical point of view. So I would like to look at this problem as a function of this control parameter sigma. And there are two cases, one in which sigma is positive, and the other one in which sigma is negative. So So let me start from the positive case. So imagine that I write this constraint as a kind of hypersphere, and I'm in 2D, so this will be my hypersphere. So this is the phase space. So so all these points here are possible assignments for this variable W. Now, if I take one of these random vectors, let me assume that this is psi mu. So each random vector essentially identifies a region in this phase space which is allowed. So for example, if sigma is positive, then the feasible portion of this phase space is just this. So let me say that this is sigma. So why this is so? Because I would like to have the scalar product between psi and W greater than sigma. So the feasible region is just this one. So you would like to have, so all vectors W's that are inside this region are good assignment for this vector. Is it clear? Okay. So this is very interesting. Why? Because here I have a kind of compact space. Each vector defines a convex portion of this space. And so my constraint satisfaction problem can be translated into saying, I would like to find what is the intersection of all these convex domains, right? So the intersection of convex domains is convex, right? So if I look at the space of solution, so here it was, I mean, I'm in 2D. So the space of solution is high-dimensional, but it's a convex thing. So it's a kind of convex polytope on the sphere. And when you increase the constraints, this convex polytope cannot do much. So if I increase the number of constraints, it can shrink. And then at some point, it can reduce to a point, and then you don't have any solution anymore. So for sigma positive, the space of solutions as a function of the density of constraints shrinks continuously to 0, but it's just a single island. Okay? Now let me consider sigma negative. Now if sigma is negative, again I take my vector psi, and then the feasible region is this one. Do you agree? But now this is non-convex. Because if I take these 2 points, I mean, I cannot, I mean, the shortest distance is this one. Okay? So the intersection of non-convex domains is in general non-convex, and if you start with something, first it looks like this. And then when you increase the number of constraints, this can start to do something like this. You start to develop bottlenecks, and then at some point it gets disconnected. So you go from this to something which is this, and each of these bubbles can disconnect, right? And each of these bubbles can have its proper Sutton-Sut transition, right? So this is what is, I mean, this is the essence of replica symmetry breaking. So these bubbles are nothing but the glassy states that I was discussing before.
What I was thinking about, what happens if sigma is smaller than 0? Then the mapping breaks down because the sigma cannot be the
yes, I agree. I mean, I put some quotes in the sense that they look the same, and they are the same not at this level. I mean, there is no equality here. It's just that when sigma is negative, your problem becomes non-convex. Okay, so the space of solution itself is non-convex. And here you have non-convexity because this function here is non-convex. So this is not a linear function. Here I'm taking a linear function. So I need to put the non-convexity somewhere else. And the way in which I do it is tuning this sigma. So sigma here is a parameter that allows me to tune my problem from something which is convex, and it will be not critical, because you just have something that shrinks to 0. And you go to something which is non-convex, and here you can have this phenomenon of this connection between a portion of phase space, and this can go on as soon as you increase the density.
This happens, this is analogous to the Gardner transition.
Yeah, so these are RSB, it's like a Gardner transition. So when you get this disconnection, it's like a Gardner transition. So this RSB is like, it's the same as what you find inside the glass of our spheres. So
what about the structure? Because in the Gardner transition, we also discussed not only the were clustered within clusters, but also the structure that somehow maintained.
the structure, what do you mean by the structure?
Okay, I'm not sure what I mean,
But
but
don't worry.
I understand how this gives us disconnected regions, but just the fact that they are disconnected, how exactly is it equivalent to the Gardner position?
That if you look at the order parameter that describes the structure of these islands and how these islands organized between themselves within the full phase space, the order parameter is again a function. In the glass case, we had this function delta of x that was summing up all this delta r that you have for each level of this RSB. And here you will have the same. So you have bubbles of bubbles of bubbles and so on. So I just wrote the first level just to give you an idea. But since this happens for a bubble like this, you can imagine that all those bubbles will undergo the same process. So this process never ends. Okay? And in particular, it cannot end when you go close to the Sutton-Sut transition. So if I fix sigma and I increase alpha, at some point there will be a point in which I'm not able to find solution anymore. And this point will be like the Jammine transition for R spheres. So I wanted just to end up with some references, just 2 minutes, because I said all this, and I mean, this is something that comes from a lot of work, and it's good to give you some references. So, okay, where do I write there? So this perceptron problem was first, okay, so this is something that started in machine learning, I think in the 50s, with works by Rosenblatt and McCulloch and Pitts. And then the statistical mechanics approach of disordered systems was done by Elizabeth Gardner, the same as the Gardner transition. And I think it was 85 something. Now I'm not sure about the date. But she analyzed the problem when sigma is positive. So she really looked at this problem, this constraint satisfaction problem, and analyzed the case where sigma is positive. So, so why she did this? Because when sigma is positive, also from a machine learning perspective, you have a good interpretation. Why? Because, I mean, sigma is just this region here. So you are just saying, I don't want my points just to be on one side, but I would like to have them far away from this line by an amount sigma. So it's some kind of measure of robustness of your machine. And now if you take sigma negative, this meaning is lost. So she didn't do the computation with sigma positive. So there is a work by Elizabeth Gardner and then Gardner and Derrida. Who analyzed also the generalization properties of this network. And then, so the case with sigma negative, so it was first, I think, okay, so it was first mentioned in the PhD thesis of Rémy Monasson. Who just realized that when sigma is negative, you can have this replica symmetry breaking phenomenon. And then it was studied in mathematics. So in math, and there is a paper by Stoschnitz in 2013, where he argues that you need to have, again, full replica symmetry breaking. And then, so the fact that this is a good model for jamming of spheres was found in a paper, was proposed in a paper by Franz and Parisi. This is 2016, I think. And so what they did is that, so they proposed the model, and they proposed that the sigma, the negative sigma is the one that you have for R spheres, meaning that you can look at the critical properties that I told you yesterday. You can rephrase them in this context, and you have exactly the same critical exponents and isostaticity at the jamming point. So in particular, so that's what they did. And then what we did with them, myself and Francesco Zamponi, is that we analyzed the spectrum of this model. So you have a cost function. You can go in the ansat phase. You can look at the Hessian of this cost function in a local minimum, and then you can compute the spectrum. And then the spectrum you get as precisely the same behavior of the one that you get for harmonic source spheres close to jamming. So a density of states that is constant at zero frequency. Okay. And then, so there is a paper, I mean, still with them, myself, and Sevelev, where we rederive the scaling theory close to the jamming point, and we show that it's the same as the one that was found in R spheres. So in R spheres, okay, so the computation of the critical exponents in R spheres was done first in 2014. It's a paper by Charbonneau, Kurchan, Parisi, myself, and Zamponi. So in this, so there is a work in Gestat, and another one, a short one in Nature.com. So here we derive the scaling theory close to the jamming point, where we derive all the critical exponents. And then in the perceptron, they argued that you get the same scaling theory, really the same. So this perceptron has the same scaling theory for jamming as infinite dimensional spheres. And the whole scaling theory is written from both sides of the transition in this paper. And this is a SciPost 2017. So the idea for the next lectures is just to tell you a bit of the details on how you can solve this problem and how you get the scaling theory.
Okay, let's thank Pierfrancesco for the nice lecture. And I'm going to ask you to save the questions for the exercise session. Maybe we can start with the questions then,
Okay, good.
because it's 10 past
Because I didn't
4.
solve my problem.
No, don't worry. And we have cough break now, and we come back at